Okay, so I'm going to start again. So this final lecture is sort of like, in a sense, both revisiting of some of the stuff we did earlier in a very nice way, particularly dependence. And also I'm going to cover a little bit of clever new stuff that you will see. So this is the outline. So the first thing, like right at the very start, we had these fun motivational examples where we were talking about multivariable interaction. So we had these chemical reaction examples. I'm going to go into them very, very shortly. So I'm going to show you how to detect more than two variables interacting. Like yesterday we talked about dependence. It's very simple. You just got two variables that are correlated or not. Now we've got three variables that are having some effect on each other, and it can be a lot more messy when you've got more than two variables. And the next thing I'm going to talk about in quite a bit of detail is detecting dependence. So yesterday we had this asynchronous dependence measure, and we had that intuition for how we got dependence. But from your standard statistics textbook, like what you will have encountered is something like Pearson correlation. Like you draw a line, if this line has a non-zero slope, you conclude that the variable is correlated. So if you're talking to practitioners and you give them HSIC and you tell them that shows whether the dependence exists or not, it's pretty hard for them to understand that. But you can arrive at it using something much more interpretable than that. Something I'm going to spend a decent amount of time on. Then right at the end we have some sort of interesting tools, slightly more quirky things. So the theme of this last part, we probably will cover, is that if you've got feature representations and probabilities, then you can use these in learning algorithms. So imagine a learning algorithm where your inputs are probability, like maybe you take samples from the atmosphere, maybe you take like a series of measurements. So you don't have a single point as your input, you have a set of points. And then you're learning from that set of points to an output, like the level of pollution in the atmosphere, or like whether the person is sick or whatever. So these representations, these feature representations of probabilities, you can also use in supervised learning. And that's something that we've been working on very recently. You can even learn where the output is a distribution, so that's something that might be interesting in calling it like a posterior probability. So that's quite fun. There's also stuff I'm definitely not going to cover. So hypothesis testing for time series. Most of real data are time series. So you might have 4x data, or you might have like the rain signals, like the rain is not an IID process. What it's doing now depends on what it did in the past, and it will correlate to what it does in the future. So if you're doing hypothesis testing, it's important to take that into account. We also have, since we have infinite dimensional means, you can also define infinite dimensional exponential families. That's something that we've done recently, and we've used that to do something like adaptive Markov chain Monte Carlo, where we learn the density is an infinite dimensional family, and then use that to adapt Monte Carlo to make this work. So that's just to give like a taste of some of the other stuff I've done in the last years, which I might not cover. Okay, so the first thing that I will cover is this multi-way interaction. Okay, so remember this example. We have like two causes, and these are both having an influence on a third effect. The causes individually have some weak influence, but in combination have a strong influence. So the example that I gave was a chemical reaction where you've got like, here is the Z variable is the rate of the reaction. The X variable might be the amount of heat to apply. The Y variable might be whether you add an enzyme or not to speed the reaction up. If you both heat the chemicals and apply an enzyme, the reaction goes much faster. But if you heat it and don't apply the enzyme, or if you apply the enzyme and don't heat it, the rate of reaction is less. So basically, like the combined effect is stronger than the individual effects. And this idea of having a combined effect stronger than individual effects is what we're trying to detect. So this is sort of an interesting mode of interaction between variables. Of course, there are others. You could have like, parent and then a child, and then a child adapted parent. But there you don't have this nice, like if you've just got a chain of variables, one influencing the next, you don't have this interesting effect where two variables in combination have a stronger effect. than the individual ones. So this is sort of what I'm getting at there. And this is the example I gave before. If you put sugar in your coffee, then it stir it, makes it slightly sweeter, but if you also stir your coffee, then it makes it much sweeter. Okay. This was a toy example with the statistical properties that I've described. So just to remind you, I've just generated my two parents independently of each other with a standard normal distribution. And then my z variable is the sign of the product with some exponential distribution multiplying it. So you can see that if you look just at the scatter plots of y and z, there's absolutely no dependence. There's no way I can predict z from y or z from x on their own. But if I compare z with the product of x and y, then there's a very strong dependence. So there is something I can say about me knowing x and y together, even though I can't say anything individually. So that's like the most extreme case of this example here. Okay. So how is it that we might attack this problem? So there are two sort of classical approaches that we might use. So the first thing is that, if we're going to establish that this B structure exists, we first want to ensure that the parents are independent. So the very first thing is that I test that x and y are independent. Yeah, but if they were not independent, then things would get more messy. And I don't want things to get messy. Okay, so I've established that x and y are independent. Now, one way to learn whether this B structure exists is to say, well, if I condition on observing z, then do x and y become dependent, right? So, for example, I have seen that my chemical reaction is fast. Therefore, I know that there must be both heat and the enzyme. So now these are correlated, these are coupled. Okay, so by observing z, I have induced dependence between x and y. So conditioned on z, x and y are not independent anymore. So if I have such a test, I can determine that these two edges exist. So is that clear? Yeah. Okay, here's another attack you could use. You could say, well, is it possible if I group x and z together, that these two together are independent of y? Like, can I break this edge here? Okay. Or could I break this edge between x and z? So like, if I group y and z together, is x independent? Or if I group x and y together, are they both together independent of z? So let's say that none of these things hold. So I reject the null here, I reject that this independence happens, and I reject that this independence happens, and I reject that this independence happens. Then these two edges must be there, because I can't break off any of my variables. Okay? So I know that x and y are independent, but I know that there is no way there's no grouping of the other two variables that I can make, which would allow me to break off the remaining variables. So if I do these tests, and I say, like, I cannot establish independence here or here or here, that means these two edges must be there. So these are two attacks we can use. Okay? Using this toy example and adding noise dimensions, so basically, like, I've got in the first dimension, this is the relation, in the rest of the dimension, it's just noise to make it a little harder. The issue is that both of these tests don't work very well. So as I have noisy dimensions, the probability that I'm missing that this B structure exists quickly goes to 1. So the probability of error goes up to 1. I'm never discovering this structure. Like in pretty low dimensions. So what I mean, pretty much closed. So this is not very good. So the question is there a way to attack this problem which doesn't require you to do either a conditional dependence test, which is just an intrinsically hard thing to do, or a series of independence tests which are in effect high dimensional because I'm testing for independence on a concatenation of two variables. This amounts to testing independence in high dimensions and the problem somehow justifies, which means that these independence tests are harder than they need to be. Okay, so to show how I'm going to attack this problem, first of all, remember what we did for independence testing, right? We found a feature representation of the joint minus the product of the marginals. And the kernel we used was the product kernel on x and y. But like this was the object that we mapped to feature space. We took this difference of the joint distribution minus product of the marginals, we mapped that to some space of features, and then we found whether the norm of the difference in the features of the joint minus the features of the product of the marginals is large. Okay, and if this norm is large, then we can be pretty sure that the variables are not independent. Okay, so what do we do with 3 variables? Well, I'm going to propose something that's a sort of generalization of this to triplet variables. But this kind of looks a little bit scruffy. So let's see actually what it means. So this thing here is called the Lancaster interaction measure, and what it does is it takes the joint, and then it subtracts from it, in the case where x was independent of y and z, it subtracts that y is independent of x and z, it subtracts off z is independent of x and y, and then adds 2 times a complete independent distribution. So why would we do this? Well, let's say that this is true, that x is really independent of y and z, okay? So then when I take this and I subtract this, well, these are actually the same, because this actually holds. So these 2 cancel. And then if x is independent of y and z, well, this term here has no edges, because I've like forced x to be independent. I mean, I know that x is independent of y and z. So this is like 3 independent variables, this is 3 independent variables, this is 3 independent variables, and I've got 2 of them. So these 3 terms cancel. So basically, if it's true that any variable is independent of the other 2, then this is going to be 0. Is that clear? Okay. So basically, like, if I can break z from x and y, or if I can break y from x and z, or I can break x from y and z, then this will be 0. So what might I be missing? And prove that if I have any of these independence relations, then my Lancaster statistic is 0. Awkwardly though, if this is 0, it needn't imply these independence relations. So here is a toy example with binary variables, and I mean I just made a big table of probabilities here, so you can verify for yourself that all of these variables are interdependent, so all of the variables are coupled with every other variable, and yet I've set this up in such a way that this is 0. My Lancaster statistic is 0. So I've got completely coupled variables for which this is 0. Okay. So this is like, well, true. So what this means for our test is the following, like, if I compute this Lancaster measure, if I compute the feature space embedding of this thing here, and it's not 0, then I can conclude that there must be edges between all the variables. Okay? So if I reject the null, if I compute this embedding and I see that it's large, I know that my variables must be all connected. I know that there must be a V structure and that is independent. If this is 0, then I can say nothing. If it's 0, they might be all connected, they might not. So if it's 0, then I have to use one of my more difficult tests. But if it's not 0, then I'm in a good position, because I'm sure that I've discovered that there's all the edges there. Okay, so now how do I compute this? What I do, like remember when I was testing independence, I used as my kernel the product of 2 kernels. So now I've got 3 variables. It turns out that it's sufficient to use the product of 3 kernels. Okay? So then I find the feature space embedding of pxyz minus pxyz minus blah, 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 this very long term. And, you know, for the h-sig, for this independence measure, there weren't too many terms when I computed this norm. But now I've got, you know, this inner product with itself. So I've got like a very large number of cross terms. So this is the table of all of them. So what this, just to tell you the notation that I'm using here, this is the dot product between the embedding of the joints and the joint, right? This K matrix is the matrix containing the kernel between all X pairs. This L matrix contains the kernels between all the L pairs, the M matrix the kernel between all the L pairs. These circles are entry-wise products, and then this plus plus means that I take the sum of all the entries of that matrix. Okay? So this seems like it would be incredibly horrible to implement, but everything all cancels, and you're left with this. So remember what the h-sig looked like. The h-sig looked like just this with this term missing, right? It's the entry-wise product of the centered K with the centered L, and I sum all the terms. So the 3-way interaction statistic looks like an h-sig with an additional variable here corresponding to my z variable. So in particular, like somehow it's not it's testing a problem of the smallest possible dimension that it makes sense to test to determine three-way interactions. Whereas when I did these three independence tests, I was sort of doing higher dimensional independence tests, which is a sort of harder problem. Okay, so this is my statistic. And on this difficult problem, suddenly we're doing way better. So this is the performance of this Lancaster statistic on this very, very tough problem that we introduced with, like, you know, in high dimensions, some complicated interaction. Okay? And you can see that the performance is very, very substantially better. So basically, like, if this test works, it's pretty much like in high dimensions, you know, the only option that works. If it doesn't work, like if the Lancaster statistic is 0, there might be some interaction, but it's going to be very hard to find if it's in high dimensions. You're going to have to use one of these tests, which are completely consistent, but which don't work in practice as well in high dimensions. Okay. So here is a version of the problem where I've made it a little bit easier for these other approaches. So what I've said is that my z variable has, with some probability, direct dependence on my x1, with some probability direct dependence on my y1, and with some probability a dependence that requires interaction between x and y. So now I've increased the strength of dependence between z and x individually, and y individually. So I've made the problem a little bit easier. Okay. So when I do that, this this approach of using three independence tests is actually doing quite a bit better now. So conditional dependence testing is always hard. So this pink one is always going to struggle because it's just a very difficult problem to do a conditional dependence test. But if you do these three relatively high dimensional independence tests, that's actually in lower dimensions doing better than the Lancaster approach. As you get into high dimensions, then the red one takes the lead again. So if you've got some like coupling between the parents and the child, which is already reasonably strong without looking at the combined effect, then this does a bit better, although this still beats it in high dimensions. Okay. The next question you might say is, well, I've done it for 3 variables now, let's write the next paper with 4 variables. That turns out to be a little bit messy, okay? And the way to understand why it might be messy is that, remember we've defined this interaction measure here as like a difference and a sum of various ways of decomposing your distribution, okay? And you can do that for 4 variables as well. And when, this is the general expression for all decomposition for any number of variables, right? So you basically pi is a partition of your variables. I've broken off, say, 1 and 3 from 2 and 4 if I'm in 4 dimensions, okay? And I do -1, so the size of the partition -1, so the size of the partition here is 3, because I've got 3 groups of variables. Then size of the partition -1 factorial, and then j pi is the thing that basically takes my distribution and factorizes it according to the partition pi. Okay? So the issue is that, let's say I've got 5 variables. This is all of the partitions that you can do. So sorry about this column here. I don't know what it's doing. It's from the so you can see that there's a very large number of partitions going on. So the number of terms in this sum is going to be very, very large, right? Like we already saw for 3 variables, the number of terms was this many. Fortunately, they cancelled. For 4 variables, you can only begin to imagine how big this table would be. For 5 variables, it's going to be astronomical. So you might then say, well, okay, but remember when we did 3 variables, everything canceled down, and it was actually something very simple. So isn't that going to be the case for 4 or 5? And it turns out not. So this trick only works for 3 variables. It doesn't work for 4. The reason is because the joint simple moments which we're computing for 3 variables amount to the joint cumulants for 3 variables. So these things here are these joint cumulants. But for 4 or more variables, it's not true. These don't coincide, and this in particular is just going to be much, much nastier to compute. So again, to give you an idea, like this is as the number of variables increases, the number of partitions you can make, like if you know about bell numbers, like it's increasing like extremely quickly. So basically, if you're testing for interactions between 3 variables, it makes sense. If you're testing for interactions between 4 or more variables, you should maybe narrow down the question that you're asking. So not just ask, is there any factorization of 4 or more variables, but ask something like, you know, are these 2 dependent on these 3, say? Or like, you know, you need to sort of like narrow down your question a bit. You can't just say like, tell me if it factorizes or don't. Yeah. Okay. You can also, just in a very simple case, like a very particular kind of factorization that you can test for a larger number of variables is total independence. So does the distribution factorize into the product of the marginals? Okay. And that one ends up actually being, that's a very tractable and straightforward one to test. This is what the statistic looks like, where basically like, you know, overall with the dimensions, I'm computing the kernels between all the pairs of variables. So I've just got a sum of products of kernels minus the product of sums of kernels. It's a pretty simple statistic. So this one is absolutely tractable. You can compute it, you can use the test, and it works pretty well. Yeah. So, you know, this is a well-defined test that you can do for high numbers of variables. And you can basically embed the joint minus the product of the marginals to get a pretty straightforward expression for that. For other, like for any kind of factorization, like that's not the kind of question you can ask for large numbers of variables. So there are questions about this? Okay, so the next thing I'm going to talk about is in quite a bit more, I guess, depth, this notion of kernel dependence measures. So I talked a little bit yesterday about, like I defined a kernel dependence measure, I showed how to make a statistical test, but this dependence measure was not very interpretable. So I'm now going to introduce a way of thinking about kernel dependence measures which I think is much more compatible with the kinds of ways that we think about it in like statistics. Okay, so this is how I introduced it yesterday. So I basically had my dependence measure, and what I was saying is that I would compute like a matrix of similarities of one view of my objects, say like, you know, this is how similar these images are. I would compute a matrix of similarities of the other view of my objects, like how similar are their descriptions, and then I would basically compute the dot product between this matrix and that matrix. So like, are 2 objects that are similar in this view, like these 2 dogs, also similar in their descriptions, like it talks about how they like to follow their nose and etc. Okay, so this is how I motivated the dependence measure. But you know, when you read a statistics textbook and you read about Pearson correlation, like looking at the correlation between dependencies within one view and another view of an object is not how you would be like conventionally asked to determine dependence. What you would do is you would try and fit a line through your data and look at the slope. If the slope is positive, you would say that they're dependent. If it's flat, yes, they not. Okay. So, you know, fitting a line through your data works great if your data have a linear dependence, but we are interested in modes of dependence which might be more general. So just in the same spirit that we used for maximum mean discrepancy, what we're going to look for now is not one function, but 2 smooth functions that maximize the covariance, right? Maximize the expectation of the joint of the function mappings of the data minus the expectations, product of expectations. Okay, so I'm looking for smooth mappings of my x and of my y such that they have a strong linear covariance. And smoothness you always need to apply, because otherwise, if I didn't apply smoothness, I could have my points completely arbitrarily and get the dependent even though they were completely independent of sound. So it's smooth, as with MMD, smoothness matters. Okay, so here's a great example of variables that are dependent but not correlated, right? So I've got this ring structure on my x and y. If I compute the linear correlation, if I fit a straight line, that straight line is going to go through the origin. So my Pearson correlation will be 0. But clearly x and y are dependent, because knowing x tells you something about where y is going to be. When x is 0, y is either -1 or 1. If x is -1, then y is 0. So they're dependent, but they're not correlated. So now here are the smooth functions that I use to reveal that these variables are dependent. So basically I have x through this function, which is kind of like folding over my plot around this y-axis. And then I map y through this function, which is like folding over through my x-axis. And then I get this plot here. Now in this plot here, after mapping x through the smooth function f and y through the smooth function g, I get a nice linearly dependent pair of variables. So I basically concluded that my variables are dependent because I can find smooth mappings of those through which I can fit a straight line. And this is nice because like this is something like that a scientist would be able to interpret. It's like you can tell them that like if you transform your data using these smooth functions, then you can get a very strong linear dependence between them. So that's something that's interpretable. So is that clear? Are there questions about this?
How do you choose those two functions?
That's the next slides. Yeah. So basically, I'm going to now sort of show you how to derive these functions. And to do that, I need to introduce in a little bit more detail the notion of covariance in feature space. Okay. To do that, I'm going to start with just covariance between vectors because for me, like Hilbert spaces always make more sense by analogy with linear algebra. And then I'm going to like show what that means when we might be in Hilbert spaces. Okay. So let's say I've got just two vectors, plain vectors, one in d dimensions, one in d prime dimensions, so they needn't be the same thing. And I'm going to ask, like, are these two vectors dependent? Right? If I had two scalars, I would just compute their correlation, but now I've got two vectors, and I'm asking, do these two vectors have a dependence? Okay. So what I can do when I've got two vectors, and like let's assume they're centered, they've got 0 units, so I don't have to write too many lines. I can compute this covariance matrix. So each entry in this covariance matrix tells me whether one coordinate of x has linear covariance with one coordinate of y, right? So an individual coordinate pair. But this matrix is d by d prime. Okay. So now I've got this matrix, and you know, if these entries in these matrix, if the entries in this matrix are large, then these particular coordinates have some high correlation. But maybe I don't want to write this d by d prime matrix. Maybe I just want a single number that summarizes how big the entries are in this matrix, just as a single number. So a way that I can do this is to find the maximum singular value. So I find unit vectors that I can project on, right? So I project from the left and from the right on a unit vector, and I find the unit vectors that maximize this projection, so the maximum singular value. If this maximum singular value is 0, then all the entries in this matrix are 0, no coordinate is correlated with any other coordinate. If the maximum singular value is not 0, then some of these entries must be big. So that means there must be some dependence between these vectors x and y. Yeah? Now, when you look at what it means to take the maximum singular value, what this amounts to is finding, like if I take because remember the CXY is the expectation of XY transpose. If I take these dot products inside the expectation, I've got then F transpose X and then, you know, Y transpose G, but I've just changed the order because these are scalars that I can, which amounts to computing just the covariance between some function of X and some function of y. What is this function of x? It's f transpose x. What is this function of y? It's g transpose y. Okay? So it's saying like, you know, find me the linear functions of my vectors that have the highest covariance. That's what taking the maximum singular value means. Okay? So these are linear functions of x, these are linear functions of y. What if I use, rather than x, what if I use features of x, features of y? And maybe I'm getting like no linear dependence between x and y. So that is what comes next. Okay? So let's say that I've got now features of x and features of y. I want to find the covariance in feature space between x and y. And I can do that because I can define like basically an outer product of features by analogy to the outer product of vectors, right? So when I had, you know, x and y, then the expectation of xy transpose was my covariance. So I've got two vectors, right? And the outer product of these two vectors is my covariance. So what does this outer product look like? It looks like a matrix, which if I multiply by another vector, amounts to taking this f and then multiplying it by this scalar, g transpose h. And it's possible to define exactly the same operation in feature space. So now I've got an outer product in feature space of f and g, and this is like an infinity by infinity matrix. And if I multiply this infinity by infinity matrix by another function, h, in the same space as g, it amounts to taking this f function and multiplying it by the scalar, which is the dot product of g and h. So when you see f plus g, you should think of it as basically fg transpose, but maybe in infinite dimensions. Okay? And so in particular, if f is a feature map of x and g is a feature map of y, then I've got my features of x, features of y transpose. If I took the expectation of that, then I might get a covariance, like a covariance in feature space. So this last point here is a rather interesting one. If you think about this thing here, you can think of this as a feature of x and y together, right? Like it's like if you sort of consider x and y together as an input, this is a sort of feature map of x and y jointly. Okay? So then you might think, well, actually, what is this feature map of x and y jointly like? What does it amount to? Like what features does it encode for x and y? And it turns out that like if I think of this as a single feature map of this x and y together, and this is a single feature map of x prime and y prime together, then these feature maps correspond to the product of the kernels. So this is sort of like, if I'm using this feature map, this outer product feature map, this is this AND operation, the AND of features of x and y. So I'm going to go back to the slides from day one, and I'm going to just remind everyone why that is. So here my feature space is finite, which is just to make life clear, right? Here is my feature of x. So remember, I've got shapes with colors here. My feature of x are these shapes, indicators of whether it's a square or a triangle. My second feature is the color, whether the color is a red or a blue color. Okay. So if I define my joint feature space of colored shapes in this way here, this amounts to taking the outer product, right? So basically, like if I'm just to clarify this, like let me think of sort of I've got an object, and x is the color of this object, and y is the shape. So y equals shape. So my first kernel only sees the shape, only sees the y information, and my first kernel only sees the shape, and the second kernel only sees the color. So you might, for instance, want to determine whether shapes and colors are correlated, like whether a square is more likely to be red. Okay, so this is the sort of intuition that you should have here. Okay, so basically, like, if my second features are sort of my y features, my first features are my x features, then this outer product of these two features amounts to basically having a matrix where each entry is an AND between each of the features and colors, each of the shapes and colors. Okay, and so this outer product of phi of x and phi of y transpose amounts to like making, in this case, just a 2x2 matrix, which has all of the combinations of the features that you see in shape and features that you see in color. And what we saw is that if we took the dot product of these shape-color combinations with the second shape-color combination, then this amounts to taking the product of the kernels. So now if we go back to the slides from today, it's the same idea. So if I've got like phi of x might be my, I've got an object, the object has two views. The first view is x, like it might be the shape. The second view is y, it might be the color. Okay? And phi of x, outer product with phi of y, gives you like a matrix, in this case, potentially an infinity by infinity matrix, where each entry is the and of, like, which is to say the product of one of the features of x and one of the features of y. So there are questions about this, because this is a recently sort of invoked explanation. Okay. So this is why, basically, like if I take this feature of the xy pair and this feature of the x prime y prime pair, it amounts to taking the product of the kernels. So this is the feature space that we've chosen to use for this covariance. Okay. So then the next question you might ask is, well, if xy transpose in feature space is infinity by infinity, if I take the expectation, I get an infinity by infinity expected matrix, but maybe that matrix, has an infinite maximum singular value. There's no reason why not, right? Because I've got an infinity by infinity matrix now. So remember that when we found the representation of a probability in feature space, we had to check that the expected norm of the features was finite. And if that's true, then we were allowed to define expected features. It means that our expected features were not infinitely long. So now we have a matrix, which is an expected outer product between features. What we want to check is whether this matrix, has a well-defined maximum singular value. Because if it doesn't, then I can't compute my, my maximum singular value as a linear dependence for it. So it turns out that if the expectation of the product of the kernels in this case is finite, then not only do we know that the maximum singular value of this is finite, we know that the sum of the squared singular values of this is also finite. So even though this is an infinity by infinity matrix, I can take the sum of the square of the singular values of this matrix, and that will still be less than infinity. So then for sure the maximum singular value will be less than infinity. So this is a check that we need to make to ensure that the expectation of this outer product is a well-behaved infinity by infinity matrix. And that's the analog to the check that we made for the mean embedding, where we were just checking that the mean was existing. Okay, so this covariance now exists. What I want to do is to compute the maximum singular value of it. Okay, and that's going to be my measure of dependence, right? So now, basically, like, I can write, just by analogy with the linear algebra case, the dot product of f and cx by g. So this is what I'm using to get my maximum singular value. I'm maximizing the dot product over f and g with unit norm. And just as I did with matrices, I can show that this amounts to taking the covariance, right, or the expected product of functions of f and f of x and g of y, where, if you remember, f of x is going to be the dot product in feature space of f and the feature map of x, right? So this is the dot product as we did for linear algebra, but we're just doing it now in the space of features. Okay. So how are we going to compute these two functions now? So here I'm defining a covariance between features of x and y, where I've also subtracted off the means, because in practice the means won't be zero in feature space, so you have to subtract them off. Okay? So I'm going to now describe how I'm setting up this optimization, right? So this is the problem that I said I would solve. I'm going to maximize the dot product of f and cxyg, subject to the norm of f being bounded by 1 and the norm of g being bounded by 1. Okay. Now, we are able to establish that f is going to be a linear combination of the points in feature space that have been centered. Okay. So, a way to sort of understand why this is so is that, like, I'm going to take the dot product of f and a sum of the outer products of these guys with those guys. So if any component of f were orthogonal to this, then it would basically vanish when I took this dot product. So I know that f has to be somehow like in the space occupied by this covariance matrix. Okay, and so then I can write my Lagrangian, which is like f cxyg minus lambda on 2, and these are my constraints on f g. So to solve this, I'm not going to go into all of the details, but I just want to give you a sense of how this thing is solved. And I'm going to write that on the board now. Let me start by defining phi tilde of xi as the feature map of xi minus its mean. Okay? So this is just to save me writing lots and lots of crap. Okay. Now I'm going to show you what this expression here is going to look like. Okay? So I've got this expression f dot producted with c hat xy, which is my empirical covariance g. Okay, my empirical covariance c hat xy is 1 on n, sum I equals 1 to n. Then this tilde notation I'm going to use xi outer producted with the tilde of yi. Yep. Okay. So now let's see what happens when I take this covariance and hit it with g. Okay, so I'm just going to write here c hat xy g is equal to 1 on n. I equals 1 to n, centered xi, outer producted with centered features yi, acting on j equals 1 to n, b to j, centered features of yj. Okay? So remember my analogy with the matrix dot product. We have this result that fg transpose acting on a vector h is f, and then the dot product of g and h. The same is true for this tensor product, so f g acting on h is f, and then the dot product in feature space of g and h. Okay? So now we're going to use this result for this tensor product acting on this set of functions, right? So what I'm going to have is that this is equal to 1 on n, I equals 1 to n, j equals 1 to n, b to j, features of xi, and then I'm going to have these are centered features of xi, then I'm going to have the centered features of yi dot producted with the centered features of yj. Okay? And this thing here is going to be basically like, I'm going to write this as k tilde. This is ij, right? Which is the kernel between the centered xi and the centered xj. So k tilde ij, I can write k tilde with some simple algebra as h times k times h, where h is a centering matrix. So h is a unit matrix minus 1 on n times an n by n matrix of 1s. Okay, so that's something you can do pretty straightforwardly. So this is, actually I'm going to write this as L rather than K, because this is, I'm using L as my matrix between y's. Okay? So I'm going to have here, like I'm going to have a sum of features of xi multiplied by these scalars. Okay? But then I'm going to hit this with an f. And when I do that, I'm going to have like an alpha j or an alpha k, and then these are going to turn into dot products as well. And they're going to turn into dot products with these terms here. So basically, like when I multiply by this f. When I take the dot product with this f, I'm going to have basically like a matrix product of L, which is the kernels between the y's, and K, which is the kernel between the x's, with some beta j and alpha j scalars multiplying this whole business. Okay? And then what am I going to get from these terms? Well, I've already derived those in previous slides, but this f is going to turn into something like alpha transpose centered k alpha. And this is going to introduce a transpose centered k beta. So when I write all this down, and I take the derivatives with respect to alpha and beta, set it to 0, solve it, I get this nice system of linear equations. So these centered k times centered L, these come from here. This centered k here comes from the norm of f. So this is how it works, basically. So this is quite nice because we've sort of taken this, infinite dimensional maximum singular value problem, and we've shown that we can solve it by just solving this finite dimensional generalized eigenvalue problem. So this is quite cool because, like, I'm finding the maximum singular value of an infinity by infinity matrix, but I can do that. I can do that just with an answer that depends only on these kernels. Okay. So, these give me my functions. My functions are the linear combinations. Like if I evaluate f of x, I'm just taking the dot product of this with x. So I've got my centering term, I've got my scalars that I solve from here. So this is how I'm getting these functions. So if you want your smooth functions that illustrate where two variables covary, even if they don't have a linear dependence, this is all I need to type to solve it. Okay, so the next question becomes, like, given that this is the dependence measure that we're using, so I should have said this is called the constraint covariance because we're maximizing the covariance subject to smoothness constraints on our functions. Okay, so given that this is our dependence measure, okay, here are two densities over x and y. One of these is harder to solve than the other. Like one of these is going to have a smaller difference than the other. Okay? So here, basically, like on this x and y, I'm saying that I've got more points in these two corners here and fewer points in these corners here. Okay, for this density here, I've got something which is a lot more like fine-grained. So I've got like more points here, then fewer here, then more here, then fewer here. So I'm getting this. Okay. So who thinks that x and y will be more dependent using COCO with this density? Who thinks this one? I will show you the answer. So here is the constraint covariance, right? So I'm looking for two smooth functions that transform these points to have strong linear dependence. Okay, so I'm mapping my x through this smooth function here. Like this is the solutions to the equations that I gave on the previous slide. I'm mapping x through this function. I'm mapping y through this function. Okay? When I map x and y through this function, I'm sort of clustering my points in the corners here. Okay? And this increases the linear correlation because if I fit a line, through these points, it's going to be like this. Okay? Now let's say that I've increased the frequency. So what I've done is this is where I started, and then I'm moving a little bit towards this. So basically, you can see that I've got a sort of interleaved set of points. So there's fewer points here, more here, fewer here, more here. And so then the functions that I have to map through become a little bit more complicated. So rather than just having a single oscillation, now they've got two oscillations. And still using these sort of two oscillation functions, I can map my points into these corners. Okay? So this is sort of like a frequency of 2. This is a frequency of 1. And this is already quite amazing. The correlation between the points here is effectively 0. There's no significant correlation. But clearly x and y are dependent. But when I map my x and y through these smooth functions, my correlation goes right up to 0.5, and it becomes significant. So using smooth functions, I'm able to transform my variables to get strongly dependent variables, even though they have no linear dependence at all to start with. Okay, now this was frequency 2. Let's see what happens when I have a frequency of 3. So now it's even more introduced. So it's like light, dark, etc. Now I've got 3 wiggles of my plot. And now it's starting to struggle a little bit, but it's actually still doing pretty well. So now I've got correlation of 0.45 using these slope functions. So it's still working. It's still detecting dependence. Frequency of 4. So now it's starting to struggle a bit. My correlation's gone down to 0.2. I don't actually remember if that's significant or not. It might still be significant. But it's for sure it's not able to push all the points into the corners anymore. Like that's no longer possible. Okay, so that's frequency 4. What about this case? So who knows what frequency this is? 0. So here, I've got x and y with absolutely no dependence at all. And here are my functions. What's perhaps something to take a little bit of care of is that the correlation that I'm getting here isn't exactly 0. So because I've only got like a finite number of points, I can still rearrange them to push up the correlation a little bit. But that correlation that you get, this residual correlation here, is going to be no more than the chance level of correlation. So basically there will be, given that you've seen this many points, I can find smooth functions that will make the correlation not 0. But this is the kind of correlation you would expect from random noise. So basically, to go back to the question we asked here, this is a harder problem than this one, because it's harder to find smooth functions that maximize the correlation when the points are very interleaved, when the high density regions are sort of very, very high frequency, than in this case, where like a very smooth function can quickly find large linear correlation. And the reason this is a harder problem than this one is because I have to find smooth functions that transform my variables. And here, there are no smooth functions because the function here would be very, very rough. Okay? Another way to think about it is, if my dependence between x and y occurs at such a high frequency, then when I see 500 points, it looks like uniform noise. It looks like a frequency of 0. So this is basically a problem where you need a lot of evidence before you're prepared to say, I'm confident that x and y are dependent. Because, just visually, I can't see any dependence between x and y from this plot. And to me, this plot here looks the same as, this case here, which is completely uniform.
Can you increase the norm of your functions?
So I could make my functions less smooth. And this would push up this correlation here, but it would also push up the chance level. Because basically, like if I made my functions less smooth, like I could make them very, very non-smooth, and I could get a perfect straight line here. But then I would get that perfect straight line whatever my points were. So like if I was doing like a significant threshold, if I was saying like what is the chance level correlation? If I had non-smooth functions, the chance level correlation would be 1. Because whatever my points, I would get perfect correlation. So basically, you can adjust the smoothness constraint, but that will also have an effect on the test threshold as well. Yeah. Are there more questions about this idea? Yeah.
What's like the CO?
This is the actual maximum singular value, the CO number. So like this gamma here is the maximum singular value. That's the constraint covariance. Yeah. So I'm like just for information, I'm including this. The thing is that this quantity here has no scale because it will just depend on the scale of the ground matrices. So correlation is something where the rho is between 0 and 1. Scopo, like to scale it, what you could do is to compare it with the test threshold. You could compare it with the if quantile of the null distribution. You could give it as a fraction of that. That would give you a scaling. So, yeah. Are there more questions about this? Okay. So here's, just as a sort of summary of what we've talked about so far. So basically, as the dependence between x and y is encoded at higher and higher frequencies, so as it becomes less and less smooth, the smooth functions achieve lower linear covariance. So this is what we saw. Like we were looking for smooth mappings to give high linear covariance. If the dependence on x and y is very non-smooth, these smooth functions cannot find high linear covariance. Okay, but this is the assumption that you're making. You're sort of saying, like, I believe that my points are smoothly related, and if my belief is correct, then I'm going to find it. If my belief is wrong, I will find it eventually. I'll just need a lot more points to do it, because I need a lot of evidence to convince myself that what I'm seeing is not just chance. But to me, just using this, I guess, intuition, it seems like a good idea to require smoothness, because otherwise, like, it's not clear how you can, fail to confuse yourself by having perfectly independent variables and yet believing that they're okay. And this constraint covariance will not be zero at finite sample sizes, as we've seen here, because you can make some rearrangement of the points. But this, as I see more and more samples from this uniform density, this thing here is going to go to zero, because I'm going to basically be nailed down. I'm not going to be able to rearrange my points to get high covariance. So as I see more points, this thing is going to go down when there is no dependence between x and y. Okay, so here's like a summary. Here maybe I should have shown the correlation, but instead I've shown the constraint covariance. You can see that as the frequency at which the dependence is encoded increases, the constraint covariance is going down. This red line here gives the average of the constraint covariance when there is no dependence, so when x and y are uniformly distributed. And you can see that for 1,500 samples, there is no, significant, this is not a formal statistical argument, but you can see that the kind of constraint covariances that you are observing are of the same order that you would expect when x and y were uniform. And this is not zero, because you can rearrange the points a little bit, but this is your sort of your chance level performance. Okay, so this is the intuition that you should have about like what kind of dependence is captured by constraint covariance. Okay, can you do better? So here is an example of x and y, which are dependent but have zero correlation. I've mapped them through these smooth functions, and I've got this nice linearly correlated set of points. But is that the only dependence that exists between x and y? Okay, so remember that I got these functions by getting the solution of an eigenvalue problem. I found the largest solution of that eigenvalue problem. So what happens if I take the next largest solution? Okay, here is the next largest solution of the same eigenvalue problem. So I'm now mapping x through this smooth function and y through this smooth function. Okay, so the correlation is 0.37. Originally I got 0.8, but this correlation is not zero, and it's still significant. So using these second functions, I've captured a mode of dependence that I did not see from my first pair of functions. So like if I'm trying to give a these variables are dependent, I should include these functions as well, because I'm saying, well, actually, if I map my functions through these, if I map my variables through these smooth functions, I'm also able to obtain dependence. And these functions are orthogonal to the first functions that I found. So even in 2 dimensions, there's multiple modes of dependence that you can detect using smooth functions. Okay? And then you might think, well, why don't I use like all of the singular values, right? Well, how do I summarize like the complete spectrum of singular values? Maybe I take the sum of the squares. Well, it turns out that the sum of the squares, the sum of the squared singular values of this covariance in feature space is just this h sig. So we've got back to h sig again. So this now gives you like a really nice interpretable idea of what h sig is doing. What it's doing is it's basically finding all of the functions which I can map my variables through to get covariance, and then I'm just taking like the sum of the squared covariances that I get. That is what HSIC is doing. So if you're using HSIC in an experiment and you want to actually see what it is that it's capturing, you could plot maybe the first couple of functions so you can see the kinds of nonlinear transforms that you're getting, which allow you to find that these variables are dependent. So this is, I think, this is something that if you're writing a scientific paper, these kinds of functions are something that, like, if you're speaking to like a biologist or a chemist, like they will be able to interpret these to understand why it is that the variables are coupled. Okay. And this is just rederiving the ATIC. This detail here, I'm not going to go into much detail of, but remember, we define this dot product in the space of the outer product of features, and remember that we found that amounted to using the product kernel in the feature space. So this is why you're getting these products and kernels everywhere here. Because the feature space that we're using when we're taking the expectation of the outer product of features of x and y amounts to using the product kernel of x and y. So if x is one view of the object, like its shape, and y is the second view of the object, like its color, that tells you if the shape and color are correlated. To give a simple example. Okay. So the next question you might ask, remember that we found with characteristic kernels that if the kernel with characteristics, the Fourier transform is vanished on an integral, then we can distinguish, two distributions. So you might think, well, do I need a characteristic kernel on this joint feature space to distinguish dependence from independence? It turns out no. It turns out that it's enough to have kernels that are individually characteristic to x and y, and that's enough. So I only need, if I've got images and captions, I only need a characteristic kernel on my images and a kernel on my captions. I don't need a characteristic kernel to the space of image caption pairs, which is a harder problem. So testing independence is harder than the general problem of testing for differences in distributions. Okay? So I also have, I think, an interesting puzzle, which is like, if you're trying to find that x and y are dependent, why not just regress from x to y? Okay, and if I regress from x to y, and I can't successfully do that regression, then wouldn't that already be enough? Because I can't predict y from x, so isn't that a good indication that x and y are independent? So a reason this doesn't work is that if I'm regressing from x to y, I'm predicting the mean of y given x, right? In this case, the mean of y given x is 0. But y still depends on x, because the variance of y given x is certainly not constant with x. Right? Here it's low, here it's high, here it's low again. So if I just try to regress from y to x, I can tell you whether the mean of y given x is dependent, but it's not going to tell me whether there exists any dependence between y and x, because some other statistic of y might depend on x even if the mean doesn't. So it's not enough just to regress. This regression, in a way, you can think of it as computing the constraint covariance, but with a linear feature space on the y space. So I'm saying I'm not allowed to nonlinearly transform my y. I'm only allowed to nonlinearly transform my x. Okay? And this comes to grief for exactly this example here, where because you can't nonlinearly transform y, the covariance between the transformation of x and y is going to be 0. Because I'm only allowed to do my x. Okay, so I think, that's this section. Okay, so are there any questions, by the way, about that covariance stuff? Okay, so we have, I think, a little bit of time. I think 15 minutes more or less, if my standing time is correct. So I'm going to give like a brief flavor of some other things you can do with these mean embeddings. In particular, I'm interested now in learning where my distribution, where I have inputs as distributions. Okay. So when you have kernels, they tell you how similar two objects are. And what we've done is that we've defined a notion of kernel for probabilities, right? Because the kernel is the dot product between features of P and features, expected features under P and expected features under Q. Okay? So I could use this kernel and I could plug it into my favorite learning algorithm. Like if my inputs were not single points, but if there were samples, like if I had samples of atmospheric pollution or samples of reading, of somebody's like iron levels in the blood or something, I can take expected features under those samples and I can compute the kernel. And then I can make an FEM that might tell me binary classification or a regression or whatever I like. Okay? But then you might think, well, is this the only kernel between probabilities that I can do? Okay? And it turns out not. And so a way to think about it is, well, on the basis of this kernel, I can also define a distance between features of P and Q. But if I have this distance, well, I can plug this into another kernel, right? So this exponentiated quadratic kernel now uses as its argument the distance between features of P and Q. So I've got like, a deep kernel on probabilities now. Because I'm basically like, this outer kernel is features of this inner set of features. So I've got features of features. And I can do that for the Laplace kernel, I can do that for whatever this kernel is, and so on. Okay? So this is quite nice. So I can define actually much richer kernels than this vanilla kernel. And in practice it turns out that, as you might expect, if you have a much bigger set of features, which is what you get when you use these fancier kernels, you're going to get better performance. Okay. So where have I used this in? I'm not going to introduce expectation propagation for you, so don't worry, not in the next 15 minutes. But I just want to tell you a problem where it's important to regress where the inputs are probabilities and the outputs are like vectors, okay? So expectation propagation is a way of doing inference in a graphical model where you're basically like, predicting, what one variable believes about itself given observations made elsewhere. Okay, so I'm saying like, where is the robot in the room, given that I've observed something on my camera, something on my wheel sensor, something here and there, okay? And the key step for this algorithm is that I receive information, I receive probability distributions from elsewhere in my graph. This might come from my wheels, this might come from my camera, this might come from my GPS. And then I put out, and given my prior belief, I put out my current belief about, say, where the robot is in the room. Okay? And this EP has as its sort of core step a rather complicated method that takes in a bunch of probabilities, multiplies them by some factor, integrates them, and then projects onto whatever form your outgoing message is. So if you want this to be a Gaussian, I need to then take this messy integral and find the nearest Gaussian to it. Okay? So this integral you can do in closed form for a few simple cases. But generally, like if you've got some very complicated representations of probabilities coming in, then your only option is to do like some very complicated numerical integration, and that's expensive. So you might think, well, if I've got a few examples where I've done that numerical integration for some incoming probabilities, then maybe I can learn a regression function to replace that complicated numerical integration with something cheap. Okay? And this is nice because, like I've just described, a way of doing regression where your inputs are probabilities. I take the expected features of those input probabilities, and then I can learn a regression function. So I do a bit of training, I take some examples of that training data, then I learn my regression function. So there's another trick that I'm going to use to make this, yep.
Sorry, can you repeat again explicitly what the input distributions are and what the output distributions are?
So the input distributions sort of contain information from elsewhere in the model. So if my graphical model was trying to locate a robot in a room, the input distributions might be information that it gets from its sensors. In the form of those input distributions, like, ideally that should take, the kind of form that reflects the information. Like I shouldn't have to force myself to have a Gaussian input if a Gaussian isn't a good measure. Like maybe a multimodal distribution is more sensible because I could be in several places in the room, say. Yeah. So incoming information are probabilities which contain some information about what the robot sees, for example. The outgoing information is what I'm trying to predict. So I'm trying to maybe tell myself where I am in the room given information that I've gathered from my sensors. So the inputs are probabilities, and the output is also a probability because the output in this case will be the parameters of my distribution at the coordinates in the room with somewhere in the same. Does that make sense?
Mm-hmm.
Okay. Yeah. So the other trick is that like when I'm doing brief regression, I need to like store all my training points. And if I've got a robot wandering around the environment, the number of training points is going to grow very, very, very fast. And eventually my robot's going to run out of memory and stuff. Okay? So I need some trick to apply these kernel methods when I'm getting this data streaming in. And the way that I'm going to do this is by using this nice intuition that we had earlier of the representation of the kernel in terms of its Fourier transform. Right? So basically, like what we discovered earlier is that we could represent the kernel as a Fourier transform of some non-negative measure in the Fourier space. So for example, when we had this domain on minus pi pi, we defined the kernel as being the Fourier transform of a Gaussian, say. And rather than basically writing the kernel explicitly, what I could do is just sample from my Gaussian in Fourier space, and then just define my kernel as a dot product of those particular Fourier features. So rather than using the kernel in closed form, I'm going to sample from the Fourier transform of my kernel. Then I'm going to define my kernel as a dot product between those features that I've randomly sampled. If I sample infinitely many frequencies, that will converge to my kernel. But I won't sample from infinitely many, I'm just going to keep finitely many of them. And so now, rather than having an implicit infinite feature space, I've got an explicit finite feature space. But if I'm trying to make my model scale to very large amounts of data, then this is one way to do it. Okay, so this is what I do. Like here is my also my kernel, where I take the expectation over. If my kernel is an exponentially quadratic, I take the expectation over Gaussian, and these are Fourier features. Then I have also a random space. Okay. So here are my explicitly defined feature vectors. What if I have rather than trying to find invariants of points, I'm finding invariants of probabilities. I just take expectations of these features. Okay. And if I have like a deep kernel where I have basically the exponentiated quadratic, where this is itself a difference in features, then I can put my explicit features here, my expected explicit features, and then I can also represent this other kernel as a set of features. So here I've got features of features. And then I have again an explicit representation of a two-level set of features of my probabilities. So this is a nice trick, which means that I can now sort of regress explicitly on these features as my inputs. And then the size of the problem that I need to solve will only be as large as the number of features that I've picked, rather than going up as the number of training samples that I've picked. So is that, like, that's reasonably brisk in production, because they're sort of time-delimited questions about what I've done here. So I've defined an explicit feature space basically by randomly sampling from the Fourier transform of my kernel, choosing those frequencies and taking the kernel as a product between Fourier features and those frequencies. So it's like an approximation to my kernel. Okay. So this is actually what we do. This next slide here basically, this is the problem we're solving. It's just logistic regression here. And this is the important slide. So basically, the computation speed is on this axis, and this is different classification problems that we're solving. So I told you earlier that one way to attack this problem is by numerical integration, and that was expensive. So what we do here in these red bars is, rather than doing numerical integration all the time, we do it a few times, and then we use that to learn this regression model using the expected features of the probabilities. And then from then on, we use that instead. And you can see that you're basically gaining time, because once your new model takes over, your computation time speeds up tremendously, because you don't have to do numerical integration anymore. But what you might worry about is that, like, if you're starting to use regression, maybe your performance actually goes down, and it turns out no. So here is the performance compared with the performance from the expected sampling method, and it's exactly the same. So basically, like, we're not losing anything by doing this regression, but we're gaining quite a bit of computation. So the sort of point of this exercise is to illustrate a case where you can regress from probability embeddings, from representations of probabilities in feature space, as a way of solving a problem in machine learning. So I'm not only doing hypothesis testing, I can also do regression using these embeddings. So are there questions about this? Yeah?
So you've now used this in EP, but could you also do, say, variational inference, where you have local variables, and then, you know, you like from the likelihood for the local variables, you get the variational distribution for the local variables. Then you learn a regression, so you don't have to do this for all the local variables.
I mean, this could be an idea. I'm not sure how it would work, but it could work. Yeah, I'm not sure.
What's the intuition that this kind of approximation is the same as MLSS?
So basically, as long as the dependence of my outgoing probability on my incoming probabilities is reasonably smooth, I'm doing basically ridge regression using these embeddings of my input probabilities, right? So ridge regression, as we know, it basically has an implicit requirement that the mapping from the inputs to the outputs is reasonably smooth. So as long as when I'm doing my numerical integration and so on, as long as, in a sense, I'm fortunate and this mapping is indeed smooth, then replacing it with regression is just going to be a faster way to get the same answer. If I've got a sharp discontinuity, I might be in trouble. A similar idea, I think, is Ryan Adams has done something similar for parameter tuning for deep networks. He basically said, well, let's see how the performance of this deep network changes as a function of the ingoing parameters, but then model that as a Gaussian process, and then I can predict the performance. If the performance varies smoothly with the parameters of my network, then my prediction will be reliable. If it doesn't, then So it's very much in the same spirit. Yeah. Using sort of regression to cache the results of extensive computations, and then to predict the results of those extensive computations elsewhere. Yeah. Okay, so I want to show one or two more slides. So in this case, what I'm going to show you as my sort of final trick is a way to predict the direction of causality using mean embeddings. So this is actually not my work, it's work by David Lopez-Haz and co-authors. The result is going to rely on the following intuition, right? Here I've got x and y, and my question is does x cause y or does y cause x? So one way that you might think I can decide, the direction of causality is to say, well, I believe that, y is f of x plus noise is a sensible model. All right? So then I'm going to predict y from x, and I know that my noise is independent of my x. So my error bars shouldn't change depending on where I have up this x-axis. But then if I regress in the other direction from x to y, then I notice that my error bar is very small here, very large here, and very small here. So basically, if I believe that this is a sensible model of my world, then doing this regression from x to y and from y to x will tell me the direction of causality. Because in one direction, the errors will be independent of the location, and in the other direction, from y to x, it won't be. Yeah? So is that intuition clear?
Well, you have to assume Gaussian noise for x.
You don't have to assume Gaussian noise, so that's an important thing. So the noise here can be anything, as long as it's independent of the x, it's fine, it works. Yep.
What if this varying errors are due to your model?
That is where it doesn't work in practice. So this is why this thing, it's a beautiful theory, but in practice, what if I made an error and I didn't fit my regression very well? Then I would have dependence on the noise in both directions, and it wouldn't work. So yeah, basically, this is a brilliant idea in theory, which is a bit unreliable in practice. Even worse, here are some real examples of cause-effect data, right? How many of those look like this? Pretty much none of them, okay? So the issue is that when we see cause-effect data in real life, it's almost never this sort of neat case that we've described. Okay. But here is something that David did, which is they thought, okay, this problem is just very hard. Okay. So why don't we do the following? We can make a lot of artificial training data of this additive kind, and we can label it, saying like x causes y or y causes x. And then we compute the mean embedding of x, the mean embedding of y, and the mean embedding of the joint. And then we use that to train a classifier, okay, on this training data, on this artificial training data. And then just for fun, we'll test it on this test set and see what happens. And it turns out that it works very, very well. So even though the training data, like there's some amount of covariance shift going on, because this test data doesn't necessarily conform well to this model, but nonetheless, these points, when embedded into these feature spaces, are closer to the right side of the decision boundary than to the wrong side. And so you're still able to classify these very reliably. So this is an instance where, like, I think surprisingly, using these expected features, this time not in a regression problem, but in a classification problem, allows you, like, to solve some very intriguing real-life problems with causality. Whereas if, I tried to use this additive noise model on this data, it wouldn't work at all. So it remains to be sort of determined why it is that this works as well as it does, but it's already surprising that it does work as well as it does. Okay. So that's the conclusion. Are there questions about this last part? My noise ending is kind of weird. Okay, so I think we have a break now, so yeah, thank you.